I'm about to ruin space exploration for you, because there's a truth buried in physics textbooks that nobody wants to face. The universe was designed to keep us apart, and it's working perfectly. The universe gave us eyes that can see distant galaxies and minds that can imagine reaching them. Then it made sure we never could. Today we will see the real reason why interstellar travel is impossible. Are you ready? Let's begin. We are living in a golden age of discovery. The James Webb Space Telescope is revealing alien worlds in stunning detail. NASA's Parker Solar Probe is touching the Sun's atmosphere. The European Southern Observatory's telescopes are finding Earth-like planets around nearby stars. We've discovered thousands of exoplanets, some of which orbit within their star's habitable zone, that Goldilocks region where liquid water could exist. We see them out there, tantalizing worlds that might harbor life, orbiting stars just a few light-years away. And yet, despite all our technological achievements, those worlds remain utterly, perhaps permanently, beyond our reach. The universe is playing a cruel joke on us. It shows us wonders we cannot touch, destinations we cannot reach, and questions we cannot answer through direct exploration. Today, we're going to explore why. We'll dive into the physics that makes interstellar travel so monumentally challenging that it borders on the impossible. We'll examine the tyranny of the rocket equation, the absolute speed limit imposed by Einstein's relativity, the deadly hazards of interstellar space, and the sheer, incomprehensible scale of the distances involved. But here's what makes this conversation fascinating. Understanding these barriers doesn't diminish our wonder, it deepens it. Because when you truly grasp the obstacles standing between us and the stars, you begin to appreciate the astonishing universe we inhabit. You realize that we are prisoners on a cosmic island surrounded by an ocean so vast that escape seems fundamentally impossible. And yet we keep dreaming, we keep calculating, we keep searching for loopholes in the laws of physics. So let's begin this journey together. Let's confront the hard truths about interstellar travel. Let's examine the walls that cage us in our solar system. And let's see if there's any hope, any possibility, any conceivable path to the stars. Because even if the answer is no, the question itself reveals something profound about who we are as a species. The first barrier we need to understand is distance. And I mean distance on a scale that your brain simply wasn't designed to comprehend. When we talk about traveling to nearby stars, we're not talking about a longer version of a trip to Mars. We're talking about something categorically different, something that exists in a realm beyond human intuition. Let's start with our closest stellar neighbor, Proxima Centauri. This small red dwarf star sits roughly 4.24 light-years away from Earth. Now, what does that actually mean? A light-year is the distance light travels in 1 year, moving at roughly 300,000 kilometers per second. In 1 year, light covers about 9.46 trillion kilometers. Multiply that by 4.24, and Proxima Centauri sits approximately 40 trillion kilometers away from us. Your brain just skipped over those numbers, didn't it? That's okay. Human minds didn't evolve to grasp such scales, so let's try to make it more concrete. The Voyager 1 spacecraft, launched in 1977, is currently the most distant human-made object from Earth. It's traveling at about 17 kilometers per second relative to the Sun. That's over 61,000 kilometers per hour. That's screaming fast by any human standard. And yet at that speed, Voyager 1 would take more than 73,000 years to reach Proxima Centauri. Think about that. 73,000 years. Modern humans have only existed for about 300,000 years. Recorded human history goes back maybe 5,000 years. The entirety of human civilization would rise and fall multiple times before Voyager 1 arrived at our nearest neighboring star. But perhaps Voyager is too slow. Perhaps with better technology, we could go faster. Let's imagine we could somehow accelerate a spacecraft to 1% of light speed, 3,000 kilometers per second. That would be nearly 200 times faster than Voyager 1. At that speed, you could circle Earth's equator 7.5 times in a single second. Surely at such an incredible velocity the stars would come within reach, right? Well, even at 1% of light speed, the journey to Proxima Centauri would still take over 400 years. That's longer than the United States has existed as a nation. Multiple generations would be born, live their entire lives, and die aboard the spacecraft before it reached its destination. And here's the thing, we can't currently accelerate anything to 1% of light speed, not even close. The fastest spacecraft we've ever built relative to the Sun is the Parker Solar Probe, which reached speeds of approximately 192 kilometers per second at its closest approach to the Sun in December 2024. That's about 0.064% of light speed. And that speed was achieved only briefly using multiple gravity assists from Venus and the immense gravitational pull of the Sun itself. Make sure to hit that subscribe button and give this video a thumbs up if you're enjoying this deep dive into the cosmos. Your support helps me continue bringing you content about the wonders and mysteries of our universe. So distance alone presents a staggering challenge. But it's not just about distance, it's about what happens when you try to cross that distance quickly. And this brings us to our second fundamental barrier, the speed of light, and Einstein's special theory of relativity. In 1905, Albert Einstein published a paper that revolutionized our understanding of space and time. He showed that the speed of light in a vacuum, roughly 299,792 kilometers per second, is an absolute cosmic speed limit. Nothing with mass can reach it, let alone exceed it. This isn't a technological limitation. It's not something we can engineer our way around with better materials or more powerful engines. It's a fundamental feature of space-time itself. Why is there a speed limit? The answer lies in how mass and energy relate to each other at high speeds. As an object with mass accelerates closer to light speed, something strange happens. Its mass effectively increases from the perspective of an outside observer. This is called relativistic mass. The faster you go, the more massive you become, and therefore the more energy is required to accelerate you further. As you approach light speed, your mass approaches infinity, and so does the energy required to continue accelerating. You would need infinite energy to actually reach light speed, which is obviously impossible. Let's put some numbers on this. Imagine we want to send a small probe, let's say it weighs just 1 kilogram, to Proxima Centauri at 90% of light speed. According to a 2025 paper published on Propulsion, even using the most optimistic propulsion concepts, the energy requirements are staggering. To accelerate that 1 kilogram probe to 90% of light speed would require approximately 4.6 times 10 to the 17th joules of kinetic energy alone. That's roughly equivalent to the total energy output of about 11,000 tons of TNT, or approximately the energy released by a moderate nuclear weapon, just to accelerate 1 kilogram. But wait, it gets worse. That calculation only accounts for the kinetic energy of the payload itself. In reality, you can't just magically accelerate a spacecraft. You need a propulsion system, which means you need fuel or some energy source. And here's where we run face first into one of the most brutal equations in all of physics, the Tsiolkovsky rocket equation. The rocket equation, formulated by Russian scientist Konstantin Tsiolkovsky in 1897, describes the relationship between a rocket's velocity change, its exhaust velocity, and the ratio of its initial mass to its final mass. The equation looks simple. Delta V equals exhaust velocity times the natural logarithm of initial mass divided by final mass. But its implications are devastating for interstellar travel. Here's what the rocket equation tells us. To achieve a given change in velocity, you need to carry fuel. But fuel has mass, and that mass needs to be accelerated too, which requires more fuel, which itself has mass that needs to be accelerated. You can see where this is going. It's a vicious cycle that creates an exponential relationship between your desired velocity and the amount of fuel you need. Let's work through a concrete example. Suppose you want to send a spacecraft to Proxima Centauri and you want it to actually stop when it gets there, so you can take pictures and send data back rather than just zip past at incredible speed. That means you need to accelerate to cruising speed, then decelerate when you arrive. Let's say you want to cruise at 10% of light speed, which would get you there in roughly 42 years. Using chemical rockets, the kind we currently use for all our space missions, the most efficient propulsion systems have exhaust velocities around 4.5 kilometers per second. To reach 10% of light speed, you'd need to change your velocity by about 30,000 kilometers per second. Plug those numbers into the rocket equation and you get a mass ratio, initial mass to final mass, of approximately e to the power of 6,667. That's a number so large it's essentially meaningless. It means that for every kilogram of spacecraft you want to deliver, you'd need 10 to the power of 2,895 kilograms of fuel. For perspective, that's more mass than exists in the observable universe. For a 1 kilogram probe, chemical rockets are clearly not going to work. But what about more advanced propulsion systems? Nuclear propulsion, for instance. The best theoretical nuclear rocket engines might achieve exhaust velocities of around 100 kilometers per second, more than 20 times better than chemical rockets. That's a huge improvement, but let's run the numbers again. With a 100 kilometer per second exhaust velocity, trying to reach 10% of light speed and then decelerate still gives you a mass ratio of e to the power of 600. That's still about 10 to the power of 260. Still completely impossible. What about ion drives, which use electromagnetic fields to accelerate ionized particles to very high speeds? The most efficient ion drives have exhaust velocities around 50 to 100 kilometers per second, similar to nuclear thermal rockets, though some experimental concepts might reach 200 kilometers per second. Even at 200 kilometers per second, and this is being wildly optimistic, you're still looking at a mass ratio of s to the power of 300, or about 10 to the power of 130. To put that in perspective, there are only about 10 to the power of 80 atoms in the observable universe. The rocket equation is often called the tyranny of the rocket equation, and now you understand why. It creates an exponential wall that becomes insurmountable as you try to reach higher speeds. Every incremental increase in velocity demands a multiplicative increase in fuel mass, and when you're trying to reach velocities that are significant fractions of light speed, the numbers spiral into the realm of physical impossibility. But let's not give up yet. Maybe we're thinking about this wrong. Maybe instead of carrying all our fuel with us, we could find another way. This is where some truly creative propulsion concepts come in. Scientists and engineers have proposed various methods to sidestep the rocket equation's tyranny, and it's worth examining a few of them to see if any offer genuine hope. First, there's the concept of antimatter propulsion. When matter and antimatter meet, they annihilate each other completely, converting 100% of their combined mass into energy according to Einstein's famous equation, E equals mc squared. This is the most energy-dense reaction possible in physics. Nothing can be more efficient. If you could somehow contain antimatter and use it as fuel, you'd get far more bang for your buck than any chemical or nuclear reaction could provide. The numbers are impressive. 1 kilogram of antimatter reacting with 1 kilogram of matter would release about 9 times 10 to the power of 16 joules of energy. That's roughly equivalent to the energy released by a 21 megaton nuclear weapon, or about 4 times the yield of the Castle Bravo test, the most powerful nuclear device the United States ever detonated. In principle, an antimatter rocket could achieve exhaust velocities approaching light speed itself, which would dramatically improve the mass ratio problem. So why aren't we building antimatter rockets? Well, there are a few tiny problems. First, antimatter doesn't exist naturally in our corner of the universe in any useful quantities. You'd have to manufacture it, and creating antimatter is breathtakingly inefficient. The current world record for antimatter production is measured in nanograms, billionths of a gram, produced at facilities like CERN over the course of years. According to estimates from 2023, producing just 1 gram of antimatter would cost approximately $62.5 trillion at current production rates and efficiencies. And that's assuming we could even scale up production, which presents its own enormous technical challenges. Second, storing antimatter is phenomenally difficult. Since antimatter annihilates instantly when it touches normal matter, you can't just keep it in a regular fuel tank. You need to contain it using electromagnetic fields in what's called a penning trap or similar device. The current record for storing antimatter is about 16 minutes for antihydrogen atoms, achieved by the ALPHA experiment at CERN in 2011, with improvements since then extending storage times to over a year in laboratory conditions. But containing enough antimatter to fuel an interstellar voyage, keeping it stable for years or decades, and then releasing it in a controlled manner to produce thrust, we're nowhere close to that capability. Third, even if you could manufacture and store enough antimatter, there's the problem of directing the energy from matter, antimatter annihilation, to produce thrust efficiently. The annihilation produces high-energy gamma rays and other particles that spray in all directions. Converting that into directed thrust with high efficiency is an unsolved engineering problem. Some designs propose using magnetic fields to direct the charged particles, but these systems would be massive and complex. The bottom line, antimatter propulsion remains firmly in the realm of theoretical concepts. It doesn't violate any laws of physics, but the engineering and economic challenges are so severe that it's difficult to imagine it becoming practical within the foreseeable future. Okay, so antimatter is out for now. What about beamed energy propulsion? This is a clever idea that tries to end-run around the rocket equation by not carrying your fuel with you at all. Instead, you leave your power source at home and beam the energy to your spacecraft, typically using a powerful laser. The most famous proposal along these lines is Breakthrough Starshot, a $100 million research program announced in 2016 by investor Yuri Milner and physicist Stephen Hawking. The concept is elegant. Build an extremely lightweight spacecraft, a tiny probe weighing just a few grams, and attach it to a large, ultra-thin reflective sail. Then hit that sail with a powerful laser array based on Earth or in Earth orbit. The momentum from the laser photons reflecting off the sail would accelerate the tiny probe to perhaps 20% of light speed, fast enough to reach Proxima Centauri in about 20 years. The numbers involved are staggering. The Breakthrough Starshot team envisions a laser array with a combined power of perhaps 100 gigawatts, about 100 large power plants worth of energy. This beam would need to be focused with incredible precision onto a sail just a few meters across, maintaining that focus over millions of kilometers as the probe accelerates. According to a 2025 paper from Cornell University, published on arXiv, achieving the energy transfer needed to accelerate even a 2-gram spacecraft to 20% of light speed would require extraordinary precision in beam focusing and sail design. But here's the thing, even if Breakthrough Starshot succeeds, and that's a huge if, it can only send tiny, lightweight probes on one-way trips. There's no way to slow down when you arrive because there's no laser array at the destination to brake against. The probe would scream past Proxima Centauri at 20% of light speed, with perhaps a few hours to gather data before racing off into interstellar space forever. And you certainly couldn't send humans this way. The acceleration forces would be lethal, and there's no room for life support systems on a probe that weighs less than a smartphone. Speaking of slowing down, let's talk about that challenge for a moment. It's something people often overlook when they dream about interstellar travel. Getting up to speed is only half the problem. If you want to actually explore a destination rather than just zip past it, you need to shed all that velocity when you arrive. And according to the rocket equation, decelerating requires just as much fuel as accelerating did. This is why in Andy Weir's novel Project Hail Mary, the protagonist states that a round-trip mission requires roughly 10 times as much fuel as a one-way trip. That's not an exaggeration. A 2025 physics discussion on stack exchange confirmed the mathematics behind this. Because you have to carry the fuel for deceleration and the return trip during your initial acceleration, the mass ratios multiply exponentially. Let me give you a concrete example. Say you're using a propulsion system with an exhaust velocity of 100 kilometers per second, an optimistic but not impossible figure for advanced nuclear or ion propulsion. You want to accelerate to 10% of light speed, 30,000 kilometers per second. The mass ratio for the acceleration phase alone is e to the power of 300, as we calculated before. Now you also need to carry the fuel to decelerate when you arrive, but that deceleration fuel has to be accelerated during the first phase, which multiplies the mass ratio. Then, if you want to return home, you need fuel for the return acceleration and deceleration, and all of that has to be carried from the start. The mass ratios stack multiplicatively, and you quickly reach numbers that make the total mass of the universe look small. If you enjoyed this exploration and want to dive deeper into these concepts, check out my other video called The Absolute Limit of Human Travel Through Space, where we examine just how far humanity might realistically venture into the cosmos using the physics we understand today. It's a fascinating complement to what we're discussing here, and it might surprise you to learn where those limits actually lie. The link is in the description and pinned on the comments. This brings us to another creative proposal, the Bussard Ramjet. This concept, proposed by physicist Robert Bussard in 1960, tries to solve the fuel problem by scooping up fuel as you go. Interstellar space isn't completely empty. It contains about 1 hydrogen atom per cubic centimeter on average. Bussard proposed using a giant electromagnetic scoop, perhaps thousands of kilometers wide, to collect these hydrogen atoms and funnel them into a fusion reactor, using the resulting energy for propulsion. It's an ingenious idea. If it worked, you wouldn't need to carry fuel at all. You'd be like a ramjet aircraft, which scoops air from the atmosphere to burn in its engines. The interstellar ramjet would never run out of fuel because it would constantly be gathering more from the surrounding space. But there are problems. First, fusion is hard. We still haven't achieved sustained, net positive fusion energy here on Earth in controlled conditions despite decades of intensive research. The closest we've come was in December 2022, when the National Ignition Facility achieved fusion ignition for the first time, but that was in a tiny pellet blasted with enormous lasers, not a continuous reactor. Building a fusion reactor that could operate continuously for decades or centuries aboard a spacecraft remains far beyond our current capabilities. Second, even if you could build a working fusion reactor, there's the problem of the scoop itself. Recent analyses, including a 2026 paper published on Exponential by researchers examining general relativity and warp drive concepts, have highlighted that the magnetic field required to collect and compress hydrogen atoms over such a vast area would be enormous. The energy required to maintain that field might exceed the energy you'd gain from fusing the collected hydrogen, especially at lower speeds when you're collecting fewer atoms per second. Some calculations suggest that the Bussard ramjet would only become efficient at velocities already close to light speed, meaning you'd need some other propulsion system to get up to speed first, which brings us right back to the rocket equation problem. Third, there's drag. As you plow through interstellar space at high speed, you're constantly colliding with hydrogen atoms, cosmic dust, and other particles. This creates friction, or drag, that opposes your motion. The faster you go, the worse the drag becomes. At some point, the drag force might exceed your thrust, creating an effective speed limit. Some studies suggest this limit might be around 10 to 20% of light speed for a Bussard ramjet, though estimates vary widely depending on assumptions about scoop efficiency and interstellar medium density. So the Bussard Ramjet, while not impossible in principle, faces severe practical challenges that make it unlikely as a near-term or even medium-term solution to interstellar travel. What about generation ships? This is a completely different approach. Instead of trying to go fast, we accept the enormous travel times and design spacecraft that can support multiple generations of humans over journeys lasting centuries or millennia. The ship becomes a miniature world with artificial gravity, closed-loop life support systems, agriculture, and everything needed for a sustainable society in space. Generation ships don't require faster-than-light travel or exotic physics. They're theoretically possible with technology that's just an extension of what we have today. You could use nuclear fusion for power, rotate the ship to create artificial gravity through centripetal force, and recycle air, water, and waste in closed ecological systems. With enough time, you could reach any star in the galaxy. It would just take a very, very long time. But generation ships face their own daunting challenges, and many of them aren't about physics or engineering. They're about biology, psychology, and sociology. Could a human society remain stable and functional over dozens or hundreds of generations confined to a spacecraft? What happens if social structures break down? What if future generations decide they don't want to continue the mission their ancestors started? How do you maintain knowledge and purpose across centuries? There are also practical concerns. The ship would need to be enormous to support a viable population, probably at least several hundred people to maintain genetic diversity. You'd need redundant systems for everything because there's no calling for help if something breaks down between the stars. Cosmic radiation would be a constant hazard requiring heavy shielding, and the energy requirements, while not as severe as trying to reach relativistic speeds, would still be substantial. Even at modest speeds like 1% of light speed, such a massive vessel would require colossal amounts of energy to accelerate. We're about 45 minutes into this journey, and we've looked at distance, the speed of light barrier, the rocket equation, and various propulsion concepts. You might be noticing a pattern. Every single approach to interstellar travel runs into fundamental physical barriers that seem almost insurmountable. But we're not done yet, because there are even more challenges we haven't discussed, hazards lurking in the darkness of interstellar space that could destroy any vessel that ventures between the stars. Let's talk about what's actually out there in the vast darkness between stars. When most people think of space, they imagine emptiness, a perfect vacuum where nothing exists. And it's true that interstellar space is incredibly empty compared to anything we experience on Earth. But empty doesn't mean safe. In fact, the interstellar medium contains hazards that become absolutely deadly when you're moving at high velocities. Remember how we said interstellar space contains about 1 hydrogen atom per cubic centimeter on average? That sounds like nothing, right? And at everyday speeds, it basically is nothing. But imagine you're traveling at 10% of light speed, 30,000 kilometers per second. At that velocity, every second your spacecraft is sweeping through 30,000 kilometers worth of space. Let's say your spacecraft has a cross-sectional area of just 10 square meters, which is pretty small. That means every second, you're plowing through 300 billion cubic meters of space, encountering roughly 3 times 10 to the power of 14 hydrogen atoms. Now, a hydrogen atom is tiny and has very little mass, but when you hit it at 30,000 kilometers per second, something dramatic happens. The kinetic energy of that collision is given by 1/2 times mass times velocity squared. At relativistic speeds, even a single hydrogen atom carries substantial kinetic energy relative to your spacecraft. A hydrogen atom has a mass of about 1.67 times 10 to the power of -27 kilograms. When it hits your spacecraft at 10% of light speed, it carries roughly 7.5 times 10 to the power of -14 joules of energy. That still doesn't sound like much, does it? But remember, you're hitting 3 times 10 to the power of 14 of these atoms every single second. Multiply it out, and that's about 22,500 joules per second hitting your spacecraft, equivalent to running 22 powerful space heaters continuously. And that's just at 10% of light speed. The energy deposited increases with the square of velocity. At 20% of light speed, you're dealing with 90,000 joules per second. At 50%, it's over 560,000 joules per second. At 90% of light speed, you're absorbing roughly 4 megajoules per second, equivalent to the power output of a small industrial facility. This energy doesn't just disappear. It turns into heat, radiation, and structural damage. Your spacecraft's hull would be constantly bombarded, heating up, eroding, potentially failing. You'd need substantial shielding just to protect against individual hydrogen atoms, and that shielding adds mass, which brings us right back to the rocket equation problem. But hydrogen atoms are actually the least of your worries. Interstellar space also contains dust grains, tiny solid particles ranging from nanometers to micrometers in size. These particles are much rarer than hydrogen atoms, but they're also much more massive. A dust grain with a diameter of just 1 micrometer might weigh about 10 to the power of negative 15 kilograms, roughly 10 million times more massive than a hydrogen atom. When one of these grains hits your spacecraft at 10% of light speed, it carries approximately 45,000 joules of kinetic energy. That's equivalent to the muzzle energy of a large artillery shell. A single dust grain becomes a hypervelocity projectile that could punch through metal, shatter components, or vaporize in a spray of plasma. And you'd be encountering these grains regularly, perhaps several per cubic kilometer of space you traverse. As you go faster, the problem gets exponentially worse. At 50% of light speed, that same dust grain carries over 1 million joules, equivalent to a quarter kilogram of TNT exploding on impact. Your spacecraft would need armor thick enough to withstand these constant impacts, and that armor would need to somehow dissipate or deflect enormous amounts of energy without itself being destroyed. Some proposals suggest using magnetic or electric fields to deflect charged particles before they hit the hull. This could work for ions and perhaps some dust grains, but many particles are electrically neutral and wouldn't be affected. You'd also need incredibly powerful field generators, which add mass and require substantial energy to operate continuously for years or decades. Other proposals involve sacrificial shielding, multiple layers of material designed to vaporize incoming particles before they reach the main hull. The problem is that this shielding itself has mass, and it gradually erodes over time. For a journey lasting decades, you'd need to carry enough shielding mass to account for all the erosion that will occur. And again, more mass means more fuel, means back to the rocket equation. There's also the radiation problem. Space is flooded with cosmic rays, high-energy particles, mostly protons, that zip through the galaxy at near light speed. These cosmic rays are produced by supernovae, pulsars, active galactic nuclei, and other energetic astrophysical phenomena. When they strike matter, they can damage DNA, increasing cancer risk, cause radiation sickness, and degrade electronic components over time. Here on Earth, we're protected from cosmic rays by our planet's magnetic field and atmosphere. Even astronauts on the International Space Station receive some protection from Earth's magnetic field, but in deep interstellar space, there's no protection whatsoever. You're exposed to the full fury of the cosmic ray background. For a short mission, a few months to Mars, for example, the radiation dose is manageable, though concerning. But for an interstellar journey lasting years or decades, the cumulative dose becomes severe. According to NASA's research on radiation exposure during interstellar missions, astronauts would likely exceed safe radiation limits within just a few years without heavy shielding. And shielding against cosmic rays is difficult because these particles are so energetic. You need substantial mass, meters of water, plastic, or other hydrogen-rich material to effectively absorb them. Once again, we're adding mass to the spacecraft, which multiplies the fuel requirements. And the shielding itself can actually make the problem worse in some ways. When cosmic rays strike shielding material, they can produce secondary radiation, showers of particles created by the initial impact. If your shielding is made of heavy elements like lead, these secondary particle showers can actually be more dangerous than the original cosmic ray. That's why proposals for radiation shielding often suggest hydrogen-rich materials like water or polyethylene, which produce fewer secondary particles. But here's another challenge. Even if you solve the propulsion problem, the fuel problem, and the shielding problem, you still have to deal with time. And I don't just mean the travel time, I mean time dilation, one of the strangest and most counterintuitive predictions of Einstein's special relativity. According to relativity, time doesn't flow at the same rate for everyone. It depends on how fast you're moving. If you're moving at a significant fraction of light speed relative to someone else, time literally runs slower for you compared to them. This isn't an illusion or a perceptual trick. It's a fundamental feature of space-time that's been confirmed by countless experiments. The amount of time dilation depends on your velocity and is calculated using the Lorentz factor, usually denoted by the Greek letter gamma. The equation is gamma equals 1 divided by the square root of 1 minus v squared over c squared, where v is your velocity and c is the speed of light. At low speeds, gamma is very close to 1 and time dilation is negligible. But as you approach light speed, gamma grows rapidly toward infinity. Let's work through some examples. At 10% of light speed, gamma is about 1.005. That means for every 100 years that pass on Earth, about 99.5 years pass for you aboard the spacecraft. The difference is small, only a few months over a century. But at 50% of light speed, gamma is about 1.155. Now for every 100 years on Earth, only 87 years pass for you. You've gained 13 years. At 90% of light speed, gamma jumps to about 2.29. Now for every 100 years on Earth, only 44 years pass for you. Time has slowed to less than half its normal rate. At 99% of light speed, gamma is about 7.09, and time slows to just 14% of normal. 100 years on Earth feels like only 14 years to you. This might sound like a solution to the interstellar travel problem. If time slows down for you at high speeds, maybe you could travel enormous distances without aging much. In principle, yes. From your perspective, the journey could be relatively short. A trip to a star 100 light-years away at 99.9% of light speed would take a little over 100 years as measured by Earth clocks, but only about 4.5 years would pass for you due to time dilation. You could theoretically travel anywhere in the galaxy within a single human lifetime, from your perspective. But there are two massive problems with this. First, you still need to accelerate to those incredible speeds, which brings us back to all the fuel and energy problems we've already discussed. Time dilation doesn't help you solve the rocket equation. Second, there's the issue of what happens back home. While only a few years pass for you, centuries or millennia pass on Earth. Everyone you knew is long dead. Human civilization has transformed beyond recognition. You arrive at your destination having sacrificed everything you left behind. This is sometimes called the twin paradox, a famous thought experiment in relativity. Imagine twin siblings. One stays on Earth, the other travels to a distant star at near light speed and returns. From the traveler's perspective, the journey might take just a few years. But when they return, they find their twin is now elderly or has died of old age, because decades or centuries have passed on Earth. The traveler has effectively journeyed into Earth's future. There's no going back. This creates profound philosophical and practical questions. Would anyone volunteer for such a journey, knowing they could never return to the world they left? Would it even make sense to send humans on such missions? Or would it be better to send artificial intelligence or robotic probes that don't care about the passage of time? There's also the issue of relativity of simultaneity, another strange consequence of Einstein's theory. Events that appear simultaneous in one reference frame don't appear simultaneous in another frame moving relative to the first. This means that as you accelerate to high speeds and then decelerate at your destination, your concept of now literally changes. What you consider to be the present moment on Earth shifts dramatically. This doesn't affect the physics of your journey, but it adds to the sense of disconnection and isolation from the world you left behind. Now you might be thinking, what about suspended animation or cryogenic sleep? Science fiction often depicts astronauts sleeping through long voyages, frozen in chambers, aging slowly or not at all. Could we do that? Well, we can't currently put humans into true suspended animation. There are organisms, certain frogs, some insects, that can survive being frozen and then revived. But human bodies don't handle freezing well. Ice crystals form inside cells, rupturing membranes and causing irreversible damage. Every cell in your body would need to be protected somehow. Some research is exploring vitrification, a process that turns biological tissue into a glass-like solid without forming ice crystals. This has been achieved with small samples of tissue, even some organs for short periods, but scaling it up to preserve an entire human body, maintaining that preservation for decades, and then successfully reviving, the person remains far beyond our current capabilities. There's no guarantee it's even possible, and even if it were, you'd still need to keep life support systems running for the duration of the voyage, protecting the frozen crew from radiation and maintaining the ship's trajectory. Another idea is to slow metabolism rather than stopping it entirely, a state called torpor, similar to what bears do during hibernation. Some research has shown that humans can be cooled slightly to reduce metabolic rate, and this is sometimes done in medical settings for a few hours during certain surgeries. But sustaining a hibernation-like state for years is completely different. We don't have the biology for it. It would likely require genetic engineering or advanced pharmacological interventions that don't yet exist. So suspended animation, while not violating any fundamental laws of physics, remains firmly in the realm of speculation and future technology. We can't count on it as a solution to the time problem. Let's step back and take stock of where we are. We've examined distance, which is almost incomprehensibly vast. We've looked at the speed of light barrier and why nothing with mass can reach or exceed it. We've confronted the tyranny of the rocket equation and why carrying fuel for interstellar journeys leads to impossible mass ratios. We've explored alternative propulsion concepts, antimatter, beamed propulsion, ramjets, generation ships, and found that each faces enormous, perhaps insurmountable challenges. We've discussed the hazards of interstellar space, particle impacts, radiation, erosion, and we've examined time dilation and the profound disconnect it creates between travelers and those they leave behind. Every single aspect of interstellar travel seems to conspire against us. The universe has constructed a labyrinth of barriers, each one formidable on its own, all of them compounding to make the stars unreachable. And we haven't even talked about navigation, communication, mission control, or what you'd actually do when you arrived at another star system. Let's talk about navigation and communication, because these present their own unique set of challenges that people rarely consider when they dream about interstellar travel. When you're crossing the void between stars, you can't just point your spacecraft in the right direction and hope for the best. The distances are so vast and the targets are moving that even tiny errors in navigation can result in missing your destination by billions of kilometers. Consider Proxima Centauri again. It's 4.24 light-years away, which is about 40 trillion kilometers. Now imagine you make a navigational error of just 1 degree, a single degree, which seems like almost nothing. Over 40 trillion kilometers, a 1-degree error translates to a missed distance of about 700 billion kilometers. For reference, that's roughly 4,700 times the distance from Earth to the Sun. You'd sail right past your destination and never even see it. Even a 1/10 of a degree error, which sounds incredibly precise, would result in missing your target by 70 billion kilometers. That's about 470 times the Earth-Sun distance, well beyond the orbit of Pluto. And we're talking about pointing a spacecraft with that level of precision while it's accelerating, while it's being buffeted by the solar wind and gravitational perturbations from planets, while it's possibly making course corrections over decades or centuries. For comparison, the Voyager spacecraft, despite being navigated with impressive precision, have drifted slightly from their predicted trajectories over the decades. This is partly due to something called the Pioneer anomaly, a small but measurable deceleration that affected both Pioneer and Voyager spacecraft, likely caused by thermal radiation from their onboard power sources, creating a tiny thrust. Scientists eventually figured this out, but it took years of analysis. Now imagine trying to account for all possible sources of thrust, drag, and perturbation over a journey lasting not decades but centuries. You'd need to make course corrections along the way, which means you need to know where you are. But how do you navigate in interstellar space? On Earth, we use GPS satellites. In near-Earth space, we can use ground-based radar and radio telescopes to track spacecraft. But between the stars, you're on your own. You'd need to navigate using pulsars, rapidly rotating neutron stars that emit regular pulses of radio waves, acting as cosmic lighthouses. This technique, called pulsar navigation, is theoretically possible and has been tested experimentally. NASA's NICER experiment on the International Space Station demonstrated pulsar-based navigation in 2017, showing that spacecraft could determine their position to within 5 kilometers. That sounds pretty good, until you remember that 5 kilometers is the margin of error, not the position accuracy you need over interstellar distances. You'd need to refine this dramatically, tracking dozens of pulsars simultaneously with extraordinary precision over years of flight. And pulsars themselves aren't perfect clocks. They gradually slow down over time, and they occasionally glitch, suddenly speeding up briefly before resuming their slowdown. You'd need detailed models of every pulsar you're using, constantly updated, to maintain accurate navigation. Then there's the communication problem. Let's say your spacecraft successfully reaches Proxima Centauri after decades of travel. You've taken incredible photographs of the system, discovered planets, maybe even detected signs of life. Now you want to send that data back to Earth. How do you do it? Radio waves travel at the speed of light. Nothing can go faster. Proxima Centauri is 4.24 light-years away, which means any signal you send takes 4.24 years to reach Earth. And if Earth sends a reply, new instructions, congratulations, questions about what you found, that reply takes another 4.24 years to reach you. The minimum round-trip communication time is 8.48 years. This creates a profound problem for mission control. If something goes wrong with your spacecraft, Earth can't help. By the time they receive your distress signal, over 4 years will have passed. By the time their advice reaches you, over 8 years will have passed. Whatever crisis occurred will long since have been resolved, one way or another. The spacecraft must be completely autonomous, capable of diagnosing and fixing its own problems without any assistance from home. And there's another issue: signal strength. Radio signals obey the inverse square law, which means their intensity decreases with the square of distance. Double the distance, and the signal becomes 4 times weaker. Triple the distance, and it becomes 9 times weaker. Over interstellar distances, this attenuation becomes severe. The Voyager 1 spacecraft, currently about 23 billion kilometers from Earth, roughly 1/5 of 1% of the way to Proxima Centauri, transmits at a paltry 23 watts, about the same power as a refrigerator light bulb. By the time that signal reaches Earth, it's been diluted across a sphere over 23 billion kilometers in radius. The power density at Earth is approximately 10 to the power of -16 watts per square meter. That's incredibly faint. You'd need a sensitive radio telescope to detect it, and we can only maintain contact with Voyager because we know exactly where it is and can point massive dishes directly at it. From Proxima Centauri, the signal would be 1,000 times fainter, perhaps 10 to the power of negative 22 watts per square meter reaching Earth. You'd need enormous radio dishes or extremely powerful transmitters to maintain communication. A 2025 study on interstellar communication suggested that maintaining a reasonable data rate, say a few kilobits per second, enough to transmit images and scientific data from Proxima Centauri, would require either a transmitter with power in the megawatt range or a receiving dish hundreds of meters across. Both options are technically feasible but enormously expensive and complex. And remember, this is for Proxima Centauri, our very closest stellar neighbor. For more distant stars, the problem scales with distance squared. A star 10 light-years away presents a communications challenge roughly 5 times worse than Proxima Centauri. A star 100 light-years away is over 500 times harder. At some point, communication becomes effectively impossible with anything resembling current technology. There's also the problem of bandwidth. The further away you are, the longer it takes to transmit data. If you're transmitting at 1 kilobit per second, extremely slow by modern standards, sending a single high-resolution image might take hours. Sending all the data from a complex scientific mission could take months or years of continuous transmission. And during all that time, you're using power, wearing out your transmitter, and hoping nothing interrupts the signal. Now let's think about what happens when you actually arrive at your destination. You've traveled for decades or centuries, overcome incredible obstacles, and finally reached another star system. What now? What are you actually going to do there? If you're traveling at any significant fraction of light speed, say 10 to 20%, which would make the journey time reasonable, you face a fundamental choice. Either you carry enough fuel to decelerate when you arrive, which multiplies your fuel requirements catastrophically, as we've discussed, or you don't decelerate, in which case you're going to scream through the target system at thousands of kilometers per second. Let's imagine you choose the latter option, a flyby mission like New Horizons' encounter with Pluto. New Horizons approached Pluto at about 14 kilometers per second and had just a few hours near closest approach to gather data. Now scale that up. At 10% of light speed, you're moving at 30,000 kilometers per second. How long do you have in the target system? Let's say the star system you're visiting is similar to our solar system, roughly 60 astronomical units across, about 90 billion kilometers from one side to the other. At 30,000 kilometers per second, you'd traverse the entire system in about 35 days. That's your entire data-gathering window, just over a month, to study everything in that system, photograph the planets, analyze their atmospheres, search for signs of life, and accomplish whatever scientific goals justified the decades-long journey. And here's the thing, 35 days sounds like a lot, but you need to consider geometry. Your trajectory is essentially a straight line through the system. Unless you're extraordinarily lucky, the planets won't conveniently line up along your path. You might pass within reasonable distance of 1 or 2 planets, but others will be millions or billions of kilometers away, too far for detailed study. Compare this to our missions within the solar system. The Cassini spacecraft spent 13 years studying Saturn and its moons. Mars rovers have been exploring the Martian surface for years. The amount of science you can accomplish with extended observation time is vastly greater than what's possible during a brief flyby. An interstellar flyby mission would return tantalizing glimpses, but leave enormous questions unanswered. So maybe you bite the bullet and carry enough fuel to decelerate. Now you can enter orbit around the target star or its planets. You can take your time, conduct thorough observations, perhaps even land probes on interesting worlds. But as we've established, the fuel requirements for deceleration are crushing. You need roughly as much fuel to slow down as you did to speed up, which approximately squares your initial fuel requirement. For any reasonable travel speed, this pushes the mass ratio into the realm of impossibility. Unless, and here's an interesting idea, you use the target star system itself to slow down. You could perform a series of gravity assists using planets in the target system to shed velocity, similar to how we use planetary flybys to change spacecraft trajectories within our solar system. This technique, called gravitational braking, could theoretically reduce or eliminate the need to carry deceleration fuel, but there are significant challenges. First, you need to know the precise positions of planets in the target system before you arrive, not just approximately, but with incredible accuracy, because you're planning maneuvers years or decades in advance. Second, the planets need to be in the right positions when you arrive. If they're not conveniently aligned for the gravity assists you need, you're out of luck. Third, each gravity assist only changes your velocity by a limited amount, typically a few kilometers per second at most. To shed tens of thousands of kilometers per second of velocity, you'd need numerous assists which might take decades to execute and would require an extraordinarily fortunate arrangement of planets. Some researchers have proposed using the target star itself for braking, diving close to the star, and using a combination of aerodynamic drag in the stellar atmosphere and magnetic fields to slow down. This is called a stellar brake or Oberth maneuver in reverse. It's theoretically possible, but would subject the spacecraft to incredible thermal and radiation stresses. You'd be skimming through the outer layers of a star, experiencing temperatures of thousands of degrees and radiation intensities that would vaporize most materials. The engineering challenges are immense. Let's talk about another rarely discussed problem: maintenance and reliability. Modern spacecraft are marvels of engineering, but they don't last forever. Moving parts wear out. Electronics degrade due to radiation exposure. Software can have bugs, materials fatigue over time, and eventually things break. The Voyager spacecraft, now nearly 50 years into their missions, are starting to fail. Instruments have shut down to conserve power. Heaters have been turned off, allowing non-critical systems to freeze. The power output from their radioactive thermoelectric generators has declined to the point where tough decisions must be made about which systems to keep running. Within the next few years, Voyager 1 and 2 will likely fall silent, unable to generate enough power to operate their transmitters. And Voyager has only traveled for about 5 decades across a tiny fraction of interstellar space. An interstellar mission to even the nearest stars would take centuries with any realistic propulsion system. How do you build a spacecraft that can operate reliably for that long? You could design redundancy into every system, backup components for everything, multiple independent power sources, self-repair capabilities. But redundancy adds mass and complexity. And even with extensive backups, centuries is a long time. Cosmic rays gradually damage electronic components, causing bit flips in computer memory and degrading semiconductor performance. Mechanical systems, bearings, valves, actuators, experience wear even if they're used sparingly. Seals degrade, lubricants break down, materials become brittle in the cold of space. Some proposed solutions involve building spacecraft with no moving parts whatsoever, entirely solid-state electronics, no mechanical components, no consumables. But this severely limits what the spacecraft can do. You need movable antennas to point at Earth for communication. You need adjustable instruments to target different objects for study. You need some way to stabilize the spacecraft's orientation, which typically involves reaction wheels or thrusters. Eliminating all moving parts would create an extremely limited, inflexible probe. Another approach is to design the spacecraft to repair itself. This could involve carrying spare parts and robotic systems capable of diagnosing failures and replacing damaged components. We're making progress in this direction. The International Space Station has robotic arms that can perform maintenance, and experimental self-repairing materials are being developed. But autonomous self-repair over centuries, in the harsh environment of interstellar space with no possibility of human intervention or resupply, that's orders of magnitude more challenging than anything we've attempted. Then there's the power problem. How do you power an interstellar spacecraft for decades or centuries? Solar panels won't work once you get more than a few astronomical units from the sun, sunlight becomes too faint to generate meaningful power. Beyond the orbit of Jupiter, solar intensity has already dropped to about 4% of what it is at Earth. By the time you're in interstellar space, the Sun is just another star, providing essentially no usable power. Most deep space missions use radioisotope thermoelectric generators, RTGs, which convert heat from radioactive decay into electricity. The Voyager spacecraft used plutonium-238, which has a half-life of about 88 years. When Voyager launched in 1977, its RTGs produced about 470 watts. Today, nearly 50 years later, they produce less than half that, and the power continues to decline exponentially. For an interstellar mission lasting centuries, you'd need a radioactive isotope with a half-life measured in thousands of years, or you'd need to accept that your power supply will eventually run out. Some long-lived isotopes exist. Uranium-235 has a half-life of over 700 million years, for example, but they produce heat much more slowly, meaning you'd need enormous quantities to generate useful power. And carrying large amounts of radioactive material creates safety concerns, especially during launch from Earth. Nuclear fission reactors are another option. These could generate substantial power for decades, potentially even centuries, if designed for very low power output. The Soviet Union flew nuclear reactors on some satellites, and NASA has tested reactor designs for space use. But reactors are complex, with many components that can fail. Fuel rods degrade over time. Control systems need to function reliably. Cooling systems must operate continuously to prevent meltdown. Building a reactor that could run autonomously for centuries is a formidable engineering challenge. Fusion reactors might be better if we could build them. Fusion fuel, deuterium and helium-3, for instance, is compact and energy-dense. A small amount could power a spacecraft for a very long time. But as we've mentioned, we still haven't achieved sustained fusion energy here on Earth under controlled conditions. Building a fusion reactor compact enough for a spacecraft, robust enough for centuries of operation, and efficient enough to provide net power gain remains beyond our current capabilities, though research continues. There's also the psychological dimension of interstellar travel, which becomes especially important if we're talking about sending humans rather than robotic probes. Imagine being confined to a spacecraft, even a large one, for decades or centuries. You're surrounded by the same handful of people, or, if you're on a generation ship, living in a closed society where everyone's roles and futures are predetermined by the mission. You can never go outside, never experience weather, never see a natural landscape. Earth is just a pale blue dot, then a faint star, then lost among billions of other stars. We have some data on psychological effects of isolation and confinement from Antarctic research stations, submarine crews, and the International Space Station. Common issues include interpersonal conflicts, depression, anxiety, sleep disorders, and cognitive decline. And those are for missions lasting months to perhaps a year or two, with the knowledge that you can return home. An interstellar journey has no such reassurance. You're committed. There's no abort option. You can't turn around and come home if things get difficult. For generation ships, the psychological challenges multiply. Children would be born into a world they never chose, raised with the knowledge that they'll spend their entire lives traveling to a destination they'll never see. Their children and their children's children will continue the journey. How do you maintain morale, purpose, and social cohesion across generations? What happens if people simply refuse to continue the mission, deciding instead to create a permanent home in space or change course to a different destination? There's also the question of genetic diversity. A population needs a certain minimum size to avoid inbreeding and maintain healthy genetic variation. Estimates vary, but most suggest you'd need at least several hundred individuals, possibly thousands, to establish a viable long-term population. And you'd need to manage reproduction carefully to prevent population booms or busts that could destabilize the ship's life support capacity. All of this assumes the journey goes according to plan. But what if it doesn't? What if the target star system, when you finally arrive, turns out to be unsuitable No habitable planets, too much radiation, something that makes settlement impossible. You've spent centuries traveling, exhausted your resources, and now what? There's no fuel to go somewhere else, there's no way home, you're simply stuck. This brings us to the question of why we'd attempt interstellar travel in the first place. What's the actual goal? If we're sending robotic probes, the objective is presumably scientific, to study other star systems, search for life, expand human knowledge. That's a worthy goal, but is it worth the enormous cost and effort? We can learn an enormous amount about exoplanets using telescopes here in our solar system or in near-Earth orbit. The James Webb Space Telescope, launched in 2021, can analyze the atmospheres of exoplanets dozens of light-years away, detecting molecules that might indicate biological activity. Future telescopes will be even more capable. In fact, you could argue that building a fleet of advanced space telescopes would yield more scientific knowledge per dollar spent than sending a single interstellar probe. Telescopes can study thousands of star systems, while a probe can visit only one. Telescopes can be upgraded, repaired, and even replaced as technology improves. A probe, once launched, is frozen in time. It carries the technology of the era it was built in and can't be upgraded. If the goal is human settlement, establishing colonies on planets around other stars, then the challenges become even more severe. You need to transport not just people but all the infrastructure to build a civilization: agriculture, manufacturing, medicine, education, governance. You need genetic diversity, skills diversity, and enough people to fill all necessary roles. You're talking about sending thousands of people on a journey that might last centuries or millennia to settle a world that you've likely never even seen up close, that might turn out to be hostile or uninhabitable, despite looking promising from a distance. And for what? Earth isn't perfect, but it's a paradise compared to anywhere else we've found. It has breathable air, drinkable water, comfortable temperatures, a protective magnetic field, a rich biosphere. Even if we catastrophically damage Earth through climate change, nuclear war, or ecological collapse, it would still be far more habitable than any exoplanet we've discovered. It would be vastly easier to fix Earth than to settle a completely alien world light-years away. Some argue that interstellar colonization is necessary for the long-term survival of humanity, that we need to spread to multiple star systems to avoid extinction from asteroid impacts, supervolcano eruptions, or other catastrophes. But this argument has problems. First, any realistic interstellar mission would involve such a tiny fraction of humanity, hundreds or thousands of people out of billions, that it wouldn't meaningfully reduce existential risk to our species as a whole. Second, the same resources devoted to interstellar travel could instead be used to detect and deflect asteroids, establish self-sufficient colonies on the Moon or Mars, or develop technologies to survive catastrophes on Earth. There's also a deeper question. Is it ethical to send people on a one-way journey to another star, knowing they'll never return, and their descendants will live their entire lives confined to a spacecraft or struggling to survive on an alien world? Do we have the right to make that choice for future generations who'll be born into circumstances they didn't choose? Now let's consider some of the more exotic proposals that attempt to circumvent the problems we've discussed. These are ideas that don't violate the known laws of physics but push right up against the boundaries of what might be theoretically possible. One such concept is the Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994. This is based on a solution to Einstein's field equations in general relativity. The idea is to contract space-time in front of your spacecraft and expand it behind, creating a bubble that moves through space faster than light, carrying the spacecraft with it. Crucially, the spacecraft itself isn't moving faster than light relative to the space-time immediately around it. Space-time itself is moving. This potentially sidesteps the speed of light limit. When Alcubierre first proposed this, it caused significant excitement. Could this be a loophole in relativity? Could faster-than-light travel actually be possible? Well, not so fast. the Alcubierre drive has some severe problems. First, it requires exotic matter, specifically matter with negative mass or negative energy density. This isn't just rare or hard to find. We've never observed anything like it in nature. There are some quantum effects like the Casimir effect that produce regions of negative energy density, but these are incredibly tiny and exist only in very specific conditions. Scaling this up to create the quantities of exotic matter needed for an Alcubierre drive, estimates suggest you'd need more negative energy than the total positive energy in the entire observable universe, is so far beyond our capabilities that it's hard to even classify it as speculative. It's purely hypothetical. Second, recent analyses of the Alcubierre metric have revealed additional problems. A February 2026 paper published on Archive by researchers Hamed Barzagar, Thomas Buchert, and Quentin Vigneron critically examined warp drive proposals and identified fundamental issues. They showed that when you apply general relativity correctly, without special assumptions or approximations, the so-called warp drive solutions face severe limitations. Many claims about their feasibility need to be reassessed. The paper proved several new no-go theorems demonstrating that physical warp drives are even more problematic than previously thought. Third, even if you could somehow construct an Alcubierre drive, there are causality problems, potential violations of cause and effect that could allow time travel and create paradoxes. Most physicists believe nature prevents such violations, which would mean Alcubierre drives are fundamentally impossible even if we could solve the exotic matter problem. Despite these challenges, research continues. A 2025 study revisited warp drive physics and proposed refined designs that might require less exotic matter, though still enormous amounts by any practical measure. In late 2025, physicist Harold White and his team at the Limitless Space Institute reported observing patterns in experimental data that resembled the energy distribution predicted by certain warp drive models. They were studying Casimir cavities, tiny spaces between microscopic metal plates where quantum effects produce regions of reduced energy density. The patterns they observed looked mathematically similar to what you'd need for a warp bubble. This generated considerable media attention, but it's important to understand what this does and doesn't mean. White's team didn't create a warp drive or demonstrate faster-than-light travel. They observed microscopic quantum effects that share some mathematical similarities with theoretical warp drive models. That's interesting from a physics perspective, but it's an enormous leap from observing quantum effects at nanometer scales to building a functioning warp drive for a spacecraft. It's like observing that water can flow downhill and concluding you're halfway to building a hydroelectric dam the size of a continent. Another exotic proposal is the use of wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe. If a traversable wormhole existed between our solar system and, say, Proxima Centauri, you could potentially step through and arrive almost instantaneously, regardless of the 4.24 light-year distance through normal space. Wormholes arise as solutions to Einstein's equations, just like the Alcubierre drive. The problem is that naturally occurring wormholes, if they exist at all, would be microscopic, unstable, and would collapse instantly. Faster than light could traverse them. To make a wormhole traversable, you'd need to somehow stabilize it and enlarge it to a size big enough for a spacecraft. And guess what that requires? Exotic matter with negative energy density, the same stuff needed for the Alcubierre drive. There's another problem. Even if wormholes exist and can be stabilized, they likely can't be created from nothing. The most realistic wormhole scenarios involve finding a naturally occurring wormhole, perhaps a remnant from the Big Bang, and then manipulating it. But we've never detected any evidence of naturally occurring wormholes, and if they existed, they'd likely be incredibly rare and randomly distributed. The odds of one conveniently connecting Earth to an interesting destination are vanishingly small. Some physicists have proposed using quantum entanglement for faster-than-light communication or even travel. Entanglement is a real quantum phenomenon where two particles can be correlated in such a way that measuring one instantly affects the other, regardless of the distance between them. Einstein famously called this spooky action at a distance, and it's been confirmed by countless experiments. However, and this is crucial, entanglement cannot be used to transmit information faster than light. When you measure an entangled particle, you get a random result. The other particle's measurement will be correlated with yours, but the correlation only becomes apparent when you compare results, and that comparison requires classical communication at light speed or slower. There's no way to use entanglement to send a message or transport matter faster than light. This isn't a technological limitation, it's a fundamental feature of quantum mechanics. What about using black holes for interstellar travel? Rotating black holes, described by the Kerr metric, theoretically have interesting properties. Some solutions to Einstein's equation suggest that rotating black holes might contain stable orbits inside the event horizon or could potentially connect to other regions of space-time. Science fiction has certainly explored these ideas, but the reality is far less encouraging. Approaching a black hole subjects you to enormous tidal forces. The difference in gravitational pull between your head and feet becomes so extreme that you'd be stretched into a long, thin stream of atoms, a process poetically called spaghettification. This happens well before you reach the event horizon for stellar mass black holes. Even if you could somehow survive the tidal forces, crossing the event horizon is a one-way trip. General relativity tells us that once inside, all paths lead inevitably to the singularity at the center. You can't escape, communicate with the outside universe, or emerge somewhere else. You simply end crushed to infinite density. Supermassive black holes, like the ones at the centers of galaxies, have gentler tidal forces near their event horizons because the curvature of space-time is spread over a larger area. You might theoretically cross the event horizon of a supermassive black hole without being immediately torn apart, but you still couldn't escape or communicate with the outside universe, and you'd eventually reach the singularity. And that's assuming general relativity perfectly describes the interior of black holes, which is uncertain. At the singularity, general relativity predicts infinite curvature and breaks down. We'd need a theory of quantum gravity to truly understand what happens there. Some speculative ideas suggest that the singularity might actually be a gateway to another universe or another region of our universe, a white hole that spews out matter. But there's no evidence for white holes, and most physicists consider them unlikely to exist. They appear in certain solutions to Einstein's equations, but probably don't occur in reality. The more likely scenario is that matter falling into a black hole is simply destroyed in a region of extreme space-time curvature that we don't fully understand. Let's return to more conventional physics and talk about another fundamental barrier, the information problem. Suppose we could somehow solve all the propulsion, energy, shielding, and navigation challenges. We send a mission to another star system and it successfully studies planets, collects enormous amounts of data, perhaps even discovers life. Now we want to send that information back to Earth. How much information are we talking about and how long does it take to transmit? Modern scientific missions generate staggering amounts of data. The Mars Reconnaissance Orbiter, studying just one planet in our own solar system, has transmitted over 400 terabits of data since 2006. The James Webb Space Telescope generates approximately 57 gigabytes of science data per day. An interstellar mission studying an entire star system with multiple planets would likely generate petabytes or even exabytes of data, millions or billions of gigabytes. Transmitting that much data over interstellar distances takes time. Let's say you have a powerful transmitter and can maintain a data rate of 1 megabit per second to Earth from Proxima Centauri. That's actually quite optimistic. It would require a transmitter in the kilowatt range and a receiving dish hundreds of meters across. At 1 megabit per second, transmitting 1 petabyte, a million gigabytes, would take about 30 years of continuous transmission. And remember, the data takes another 4.24 years to actually reach Earth after it's transmitted, traveling at light speed. So you're looking at decades between when data is collected and when scientists on Earth can analyze it. For a human crew, this creates profound frustration. You make a discovery, you're excited to share it, and you know that no one on Earth will know about it for years. Any questions they have about your findings take over 8 years round trip to answer. Scientific discussions that might take hours in a laboratory on Earth stretch out over decades in interstellar space. There's also the problem of data compression and prioritization. You can't transmit everything, so you need to choose what's most important. But how do you decide what matters when you're studying a completely unknown star system? You might focus on one type of data, only to later realize you missed something crucial. And once you've moved on or exhausted your power budget for transmission, that information is lost forever. Now let's discuss stellar neighbors and what we actually know about nearby star systems, because this affects whether interstellar travel would even be worthwhile. As of February 2026, astronomers have confirmed over 5,000 exoplanets, with thousands more candidates awaiting verification. Some of these orbit stars relatively close to us. Proxima Centauri, our nearest neighbor, has at least 2 confirmed planets, Proxima Centauri b, discovered in 2016, and Proxima Centauri d, confirmed in 2022. Proxima b orbits in the star's habitable zone, the region where liquid water could exist on a planet's surface. It's roughly Earth mass, which initially generated enormous excitement. Could this be an Earth-like world just 4 light-years away? Unfortunately, there are problems. Proxima Centauri is a red dwarf star, much smaller and cooler than our Sun. For a planet to be in the habitable zone, it needs to orbit very close to the star. Proxima b orbits at just 0.05 astronomical units, about 12 times closer than Earth is to the Sun. At that distance, the planet is likely tidally locked, meaning one side always faces the star, while the other side is in perpetual darkness. One hemisphere would be scorching hot, the other frozen, with only a narrow twilight zone between them potentially habitable. Worse, red dwarfs are prone to violent stellar flares, sudden eruptions of radiation and charged particles. Proxima Centauri exhibits particularly strong flaring activity. A large flare in March 2017 increased the star's brightness by a factor of 1,000 for several minutes. Such flares would bathe any nearby planets in intense ultraviolet and X-ray radiation, potentially stripping away atmospheres and sterilizing surfaces. It's unclear whether life could survive under such conditions. The Alpha Centauri system, slightly more distant at about 4.37 light-years, consists of 3 stars. Alpha Centauri A and B, a binary pair similar to our Sun, and Proxima Centauri, which orbits the binary pair at a large distance. In 2016, a planet candidate called Alpha Centauri b was announced orbiting Alpha Centauri b, but this was later retracted. The signal was likely noise in the data. As of 2026, no confirmed planets have been detected around Alpha Centauri A or B, though searches continue. Barnard's star, 6 light-years away, was thought to have a planet, but that detection is now disputed. Tau Ceti, 12 light-years distant, might have several planets, including possibly 2 in or near the habitable zone, but these remain unconfirmed. The sad reality is that while we've found thousands of exoplanets, we know very little about most of them. We can estimate their mass or size, orbital period, and sometimes get crude information about their atmospheres. But we don't know if they have magnetic fields, plate tectonics, moons, stable climates, or any of the other factors that might make them suitable for life or human settlement. Sending an interstellar mission to a world we've barely characterized is an enormous gamble. You're committing centuries of effort and vast resources based on fragmentary data. The planet that looks promising from 4 light-years away might turn out to be a hellscape when you arrive. A toxic atmosphere, lethal radiation, Extreme temperatures, violent weather, no water, unsuitable gravity. And there's no plan B. You can't just go somewhere else. This brings us to an important philosophical question that often gets overlooked in discussions about interstellar travel. What exactly are we trying to achieve? Is the goal to physically visit other star systems with human explorers, to establish permanent settlements, or simply to gather information about the universe? Because depending on your answer, interstellar travel might not even be necessary. Consider what we've accomplished with telescopes. The Hubble Space Telescope, launched in 1990, revolutionized our understanding of the universe from its position just 547 kilometers above Earth's surface. The James Webb Space Telescope, positioned at the second Lagrange point about 1.5 million kilometers from Earth, can analyze the atmospheric composition of exoplanets dozens or even hundreds of light years away. It does this by observing how starlight filters through a planet's atmosphere during transits, revealing the chemical signatures of various molecules. In 2023, JWST detected carbon dioxide in the atmosphere of WASP-39b, a gas giant about 700 light-years away. In 2024, it identified possible biosignature molecules in the atmosphere of K218b, a planet 120 light-years distant. These are staggering achievements. We're analyzing the air of worlds so distant that their light takes over a century to reach us, and we're doing it from the comfort of our own cosmic neighborhood without needing to travel anywhere. Future telescope concepts push this even further. A proposal called the Solar Gravitational Lens mission would use the sun's gravity as a giant magnifying glass. Einstein's general relativity predicts that massive objects bend space-time, and this bending acts like a lens. If you position a spacecraft at about 550 astronomical units from the Sun, roughly 14 times Neptune's distance, you can use the Sun's gravitational lens to magnify distant objects by factors of billions. A telescope at that distance could theoretically image exoplanets with resolution measured in kilometers, allowing us to see continents, oceans, clouds, maybe even cities if they exist. Getting to 550 astronomical units is challenging. It would take decades with current propulsion, but it's vastly easier than interstellar travel. And from that vantage point, we could study countless star systems in extraordinary detail without ever leaving our solar system. We could search for techno-signatures, signs of technological civilizations, by looking for artificial lights on night sides of planets, atmospheric pollution from industry, heat signatures from energy generation, or even megastructures like Dyson swarms. So one could argue that physical interstellar travel is unnecessary for learning about the universe. Telescopes and remote sensing can tell us almost everything we want to know. Why risk human lives, spend astronomical sums of money, and overcome nearly impossible technical challenges to physically go somewhere when we can study it from here? The counter-argument is that there are things you can only learn by being there. A telescope can tell you the chemical composition of a planet's atmosphere, but it can't explore caves where unusual life might hide. It can't drill beneath the ice of an ocean world. It can't sample rocks, study geological formations up close, or search for fossil evidence of past life. It can't respond flexibly to unexpected discoveries, shifting focus to investigate something surprising. And it certainly can't establish a human presence, a permanent settlement, a backup location for humanity. These are valid points. There's something irreplaceable about direct exploration, about boots on the ground, about the human capacity to observe, adapt, and discover in ways that robots, no matter how sophisticated, cannot fully replicate. Every successful planetary mission in our solar system, from Apollo moon landings to Mars rovers, has revealed surprises that couldn't have been anticipated from remote observations. But here's the brutal truth: the universe doesn't care about what we want. It doesn't matter how strongly we desire to explore other star systems or how important we believe it is. The laws of physics don't bend to accommodate human dreams. And those laws present barriers so severe that interstellar travel might remain forever beyond our reach. at least with any technology we can currently envision or extrapolate from known physics. Let's take stock of everything we've discussed. The distances are almost incomprehensibly vast. Crossing even to the nearest stars would take decades at best, centuries more realistically. The speed of light imposes an absolute limit, and approaching it requires infinite energy. The rocket equation creates exponential fuel requirements that quickly become physically impossible. Alternative propulsion concepts, antimatter, beamed propulsion, fusion ramjets, all face enormous technical challenges. Exotic solutions like warp drives and wormholes require matter and energy forms we've never observed and may not exist. Even if we solved propulsion, we'd face deadly hazards, particle impacts at relativistic speeds, cosmic radiation, equipment failures over century-long journeys. Time dilation would disconnect travelers from everyone they left behind, sending them into humanity's future with no way back. Navigation and communication over interstellar distances present their own formidable challenges, and the destinations themselves might turn out to be unsuitable, despite appearing promising from a distance. Each of these barriers alone would be daunting. Together they form a wall so high that it's difficult to see how we could possibly climb it. And this leads to a sobering conclusion. Perhaps interstellar travel isn't just currently impossible with our technology, but fundamentally impossible. Perhaps the universe is structured in such a way that intelligent species are confined to their home star systems, able to observe the cosmos, but never to physically explore it beyond their local neighborhood. This is sometimes called the Great Filter Hypothesis in the context of the Fermi paradox. Enrico Fermi famously asked, "If the universe is vast and ancient, filled with billions of stars and planets, where is everyone? Why haven't we detected any signs of alien civilizations?" One possible answer is that there's some barrier, some filter, that prevents civilizations from expanding across the galaxy. Maybe that filter is behind us. Perhaps the origin of life or the evolution of intelligence is incredibly rare. Or maybe the filter is ahead of us. Maybe interstellar travel is the filter. If the laws of physics make interstellar travel functionally impossible, then every civilization, no matter how advanced, remains confined to its home star system. They can build powerful telescopes, detect planets around distant stars, even communicate via radio across light years if they happen to overlap in time. But they can never meet, never physically explore each other's worlds, never establish galactic empires or federations. The universe becomes a cosmic archipelago, countless island civilizations separated by uncrossable oceans. This is a melancholy thought. We're surrounded by wonders we can see but never touch. We've discovered thousands of worlds, each unique, each potentially harboring its own story. Some might be alive with ecosystems we can barely imagine. Others might host civilizations asking the same questions we are, staring at their night sky and wondering if they're alone. And yet we may be fundamentally unable to reach them. But let's not descend into complete pessimism yet, because there are some scenarios, some possibilities, however remote, that might offer hope. Let's explore a few of them. First, there's the possibility that our understanding of physics is incomplete. This has happened before. Newtonian mechanics seemed complete and absolute until Einstein revealed that space and time are relative, that mass and energy are equivalent, that gravity is the curvature of space-time. Quantum mechanics introduced even stranger concepts. Particles existing in superposition, uncertainty as a fundamental principle, entanglement connecting distant objects. Could there be another revolution in physics that reveals new possibilities for faster-than-light travel or circumventing the enormous energy requirements? It's not impossible. We know our current theories are incomplete. General relativity and quantum mechanics are both extraordinarily successful in their domains, but they're incompatible with each other. At the scales where both quantum effects and gravity become important, near black hole singularities during the Big Bang, our theories break down. We need a theory of quantum gravity, and we don't have one yet. String theory, loop quantum gravity, and other approaches attempt to unify these frameworks. Maybe one of them will reveal new physics that opens doors currently closed. Maybe space-time has additional dimensions we can't perceive, and traveling through those dimensions could shortcut the distances in our familiar 3 dimensions. Maybe there are exotic forms of matter or energy that exist under extreme conditions we haven't yet explored. But here's the thing, hoping for new physics to save us is just that, hope. It's not a plan, it's not something we can count on. Every time physics has been revolutionized, it's been because evidence forced us to expand our theories. We observed phenomena that couldn't be explained by existing frameworks, which led to new insights. Right now, we don't have any observations that suggest faster-than-light travel is possible. Quite the opposite. Every observation confirms that light speed is a hard limit. Betting on undiscovered physics to enable interstellar travel is like an ancient civilization hoping for magic carpets because they can't imagine how to fly. Eventually, humans did achieve flight, but it happened by working within the laws of physics, not by violating them. We built wings that generated lift, engines that produced thrust. We didn't develop anti-gravity or teleportation. Similarly, if interstellar travel becomes possible, it will likely be through clever engineering within known physics, not through discovering loopholes that let us ignore fundamental limits. Second possibility, maybe we're thinking about this wrong. Maybe the solution isn't to transport biological humans across interstellar distances. Maybe we should send information instead. You could transmit the complete blueprint for a human being, every genetic sequence, every cellular structure, across space at light speed. Upon arrival at the destination, advanced robotics and biotechnology could reconstruct humans from local materials. You'd be sending the recipe for humanity rather than actual humans. This is sometimes called the Starship or Seed Ship approach. You send a highly sophisticated automated factory, a von Neumann probe, that can land on a suitable world, gather resources, and begin manufacturing infrastructure, including artificial wombs, to grow humans from stored genetic templates. The humans who eventually emerge would be genetically human but would be raised by AI systems in an alien environment, never having known Earth. The information approach is intriguing because information can travel at light speed. You don't need to accelerate massive objects or carry fuel. A sufficiently powerful transmitter could send terabytes of data across interstellar distances. The challenge shifts from propulsion to information storage and reconstruction. You'd need to encode everything necessary to rebuild human civilization, not just genetic data, but knowledge, culture, technology, instructions for building the infrastructure needed to support human life. But this raises profound philosophical questions. Are the humans created at the destination really us? If you transmit your own genetic blueprint and a copy of you is constructed at Alpha Centauri, is that copy you? Or is it a different person who happens to be identical? What about consciousness? Does it transfer with the information, or do you die, and a new being with your memories comes into existence? These are questions of personal identity that philosophers have debated for centuries, and there are no clear answers. There's also a practical concern. The receiving end of such a mission would need incredibly advanced technology, nanotechnology, biotechnology, artificial intelligence, far beyond what we currently possess. You'd essentially need to send a general-purpose manufacturing system capable of building anything, including itself. This is the concept of a von Neumann probe, named after mathematician John von Neumann, who studied self-replicating machines. Von Neumann probes are theoretically possible, but represent such advanced technology that they're sometimes used as a test for the Fermi paradox. If self-replicating probes are possible, an advanced civilization could send them out to explore and colonize the galaxy. Even at modest sublight speeds, such probes could spread throughout the entire Milky Way in just a few million years, a blink of an eye in cosmic terms. So where are they? Why hasn't Earth been visited by such probes from alien civilizations? Maybe because building them is harder than we think, or maybe because they simply don't survive the journey. A third possibility: maybe we should abandon the idea of interstellar travel in human timescales and instead think in terms of deep time. What if we accepted that interstellar journeys will take not centuries but tens of thousands or even millions of years? What if we sent missions knowing that they wouldn't arrive for longer than human civilization has existed? This seems absurd at first. Why would any society invest in a mission whose results won't be known for geological timescales? But consider the timescales on which the universe operates. Stars live for billions of years. Galaxies persist for trillions of years. Against this backdrop, even a million-year journey is brief. And if you could somehow preserve a spacecraft and its cargo for such durations, perhaps using passive systems with no moving parts, radiation-hardened materials, and trajectories calculated to avoid hazards, you could eventually reach any destination. The challenge is maintaining anything functional over such timescales. Continental drift happens faster than these journeys. Species evolve. Ice ages come and go. Human civilizations rise and fall. The spacecraft would need to be essentially immortal, immune to damage, capable of functioning after eons of exposure to cosmic radiation and micrometeorite impacts. Some proposals suggest using large solid objects as interstellar transport, hollowing out asteroids or even small moons, filling them with whatever you want to preserve, and setting them on trajectories toward distant stars. The mass of rock provides radiation shielding and protection from impacts. The journey takes millions of years, but eventually the object arrives. If it contains preserved biological samples, genetic information, or even frozen embryos protected by kilometers of rock, they might survive the journey. But who's waiting at the destination to receive this cargo? You'd need to either send multiple missions, some fast, carrying equipment to establish a receiving station, others slow, carrying the precious cargo, or hope that the destination system naturally has conditions suitable for the cargo to self-activate and bootstrap a civilization. Neither seems particularly feasible. A fourth possibility: perhaps the answer lies in not traveling at all, but in transforming ourselves. If we could upload human consciousness into computers, achieving what's sometimes called digital immortality, then the constraints of biological life disappear. A digital consciousness doesn't need air, water, food, or radiation protection. It doesn't age. It can be transmitted as information at light speed or carried on robust storage media that can survive harsh conditions. This is pure speculation, of course. We don't understand consciousness well enough to know if uploading is even theoretically possible. Is consciousness a computational process that could run on different substrates, or is it fundamentally tied to biological neurons? Can subjective experience, qualia, the redness of red, the painfulness of pain, exist in a digital system? These are open questions in philosophy of mind and neuroscience. Even if consciousness uploading is possible in principle, the technology required would be staggering. You'd need to map every neuron, every synapse, every relevant molecular interaction in a brain, hundreds of trillions of connections. You'd need computational substrate powerful enough to simulate all of this in real time. And you'd need to do it without destroying the original brain if you want the person to survive the process. Otherwise, from the original person's perspective, they simply die, and a copy of them wakes up elsewhere. Let's consider another angle entirely. Maybe interstellar travel isn't impossible, just prohibitively expensive for individual civilizations. But what if multiple civilizations collaborated? If the galaxy hosts thousands or millions of technological species, perhaps they could pool resources for joint exploration missions. The costs spread across many worlds might be manageable where it would be impossible for one world alone. This assumes, of course, that such civilizations exist and that they can communicate and cooperate across interstellar distances. Given that we haven't detected any clear evidence of alien civilizations despite decades of searching, this seems optimistic. The Fermi paradox looms large. If the galaxy is ancient and vast, and if technological civilizations are common, we should see evidence everywhere. The silence suggests either that civilizations are incredibly rare or they're common but don't engage in the kind of activities, radio transmissions, starship travel, megastructure construction, that would be detectable across interstellar distances. Let's talk about something we haven't fully addressed yet: the economics of interstellar travel. Even if we could technically accomplish it, could we afford it? What would be the cost of mounting an interstellar mission? It's difficult to estimate precisely because we're talking about technology that doesn't exist yet, but we can make rough approximations. The International Space Station cost approximately $150 billion over its construction lifetime. The James Webb Space Telescope cost about $10 billion. The Apollo program, adjusted for inflation, cost roughly $280 billion. These are all within solar system projects. An interstellar mission would be orders of magnitude more complex and expensive. You'd need to develop entirely new propulsion systems, advanced life support for decades or centuries, sophisticated autonomous systems, heavy radiation shielding, and communication technology capable of operating across light years. A realistic estimate might be in the trillions of dollars, a substantial fraction of global GDP. And for what return? With terrestrial or even near-Earth projects, the benefits are relatively immediate. Communication satellites enable global connectivity. GPS provides navigation. Earth observation satellites help with weather forecasting, agriculture, disaster response. Even pure science missions like Webb or Hubble return spectacular images and revolutionary discoveries within years of launch. An interstellar mission offers no such timely returns. The journey takes decades at minimum, centuries more realistically. The data takes additional years to travel back at light speed. You're asking a civilization to invest enormous resources in a project whose payoff won't be realized for generations or centuries. What government or organization would commit to that? How do you maintain funding and public support over such timescales? Human institutions rarely think in century-long timescales. Governments change, priorities shift, funding gets redirected to more immediate concerns. Even long-term projects like cathedrals, which sometimes took generations to complete, had the advantage that people could see visible progress. An interstellar mission offers nothing but decades of waiting after the initial launch. Some argue that this is precisely why interstellar exploration should be pursued, because it forces us to think long-term, to invest in humanity's future beyond our lifetimes. It's a compelling philosophical argument, but philosophy doesn't pay bills unless the economic case can be made, or unless human nature fundamentally changes to value deep future outcomes as much as immediate returns. It's hard to see how interstellar missions get funded. There's also the opportunity cost to consider. The resources devoted to an interstellar mission could instead address pressing problems on Earth: climate change, poverty, disease, education. They could fund missions throughout our solar system, establishing bases on the Moon and Mars, mining asteroids, exploring the ocean worlds of Europa and Enceladus. The scientific return per dollar invested in these closer targets is likely far higher than for interstellar missions. Now let's address something that might seem contradictory. We've spent this entire discussion explaining why interstellar travel is effectively impossible, yet 5 spacecraft launched from Earth, Pioneer 10 and 11, Voyager 1 and 2, and New Horizons, have already achieved escape velocity from the solar system. They're technically engaged in interstellar travel right now. Doesn't that contradict everything we've said? Not really. These spacecraft are indeed traveling through interstellar space, but calling them interstellar missions is generous. They're coasting at modest speeds. Voyager 1, the fastest, is moving at about 17 kilometers per second relative to the Sun. At that speed, it would take 73,000 years to reach Proxima Centauri if it were headed in that direction, which it's not. Voyager 1 is heading toward the constellation of Ficus and will pass within about 1.6 light-years of the star. Gliese 445 in about 40,000 years. These spacecraft are essentially dead. They'll fall silent within the next few years as their power runs out. They're not controlled missions aimed at specific targets. They're artifacts, messages in bottles drifting through the cosmic ocean. They demonstrate that we can send objects into interstellar space, but they don't demonstrate anything like the kind of purposeful interstellar travel we've been discussing. True interstellar travel, missions that reach specific target stars within reasonable time frames that can conduct meaningful science that could potentially carry humans, remains in the realm of distant aspiration. The Voyager spacecraft, while representing incredible achievements, also highlight the magnitude of the challenge. They've been traveling for nearly 50 years and have barely entered interstellar space, having crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, only recently. They've traveled about 0.03% of the way to Proxima Centauri. Let me paint a picture that really captures the scale we're dealing with. Imagine shrinking the solar system down so that the Sun is the size of a basketball. On that scale, Earth would be about the size of a peppercorn, orbiting 26 meters away from the basketball Sun. Neptune, the outermost major planet, would be circling at a distance of about 800 meters, roughly half a mile. The Voyager spacecraft, after nearly 50 years of travel, would have made it to about 1.5 kilometers from our basketball Sun. Now, on this same scale, where would Proxima Centauri be? About 7,000 kilometers away. That's roughly the distance from New York to London. Our fastest spacecraft, after 5 decades of travel, has covered less than a mile. The nearest star is in another country. The magnitude of interstellar distances becomes visceral when you visualize it this way. We're not even close to having traveled interstellar distances in any meaningful sense. There's another sobering consideration we should discuss: the generational knowledge problem. Suppose we launched an interstellar mission today with the expectation that it would reach its destination in, say, 200 years. That's roughly 8 human generations. Over those 2 centuries, will humanity maintain the expertise and infrastructure needed to communicate with and operate the spacecraft? Languages change over centuries. Technical knowledge can be lost. The organizational structures that built and launched the mission will long since have dissolved. Consider that we've already lost some of the expertise that enabled the Apollo missions. Detailed knowledge of Saturn V rocket construction, for instance, exists now mainly in archived documents because the engineers who built those systems have passed away and the facilities have been repurposed or demolished. Now extend that to 2 centuries. Will the people of the 23rd century even understand the technology of our era? Will they care about a mission their great-great-great-grandparents launched? Will the receiving infrastructure, the massive radio telescopes needed to detect faint signals from light years away, still exist and be maintained? Or will the mission arrive and transmit its findings into the void with no one listening? This isn't idle speculation. We've seen terrestrial examples of long-duration projects failing due to generational knowledge loss. Nuclear waste repositories must remain secure for tens of thousands of years, longer than recorded human history. How do you communicate danger to civilizations that might not speak any language we recognize, that might not even be human? The problem of maintaining institutional continuity over centuries or millennia is profound. Let's also address the ethical dimensions more deeply. Suppose we develop the technology for generation ships, spacecraft that could support human populations over multi-century journeys. Who gets to go? How do you select the initial crew, knowing they're volunteering not just themselves but all their descendants for a life confined to a spacecraft? What rights do those future generations have? Can they choose to abort the mission, turn around, or alter course? Or are they morally bound to complete a journey their ancestors began? There's also the question of what happens if the mission fails. If a generation ship suffers a catastrophic failure midway through its journey, life support fails, a plague breaks out, social structures collapse, everyone aboard dies. We've sent them to their deaths. Is it ethical to create that risk, especially for people who'll be born aboard the ship and never consented to the journey. And what about the destination? If we find a habitable world and establish a colony, what are our ethical obligations to any existing ecosystems? If the planet harbors microbial life, do we have the right to introduce Earth organisms that might outcompete or destroy native life? The history of colonization on Earth is filled with ecological disasters where introduced species devastated native ecosystems. Do we want to become the invasive species of the galaxy? Even on sterile worlds without life, there are questions. By establishing ourselves on another planet, we're forever changing it. We're taking a world that evolved naturally over billions of years and remaking it to suit our needs. Some philosophers argue we have a responsibility to preserve natural environments even on lifeless worlds, that not everything in the universe should be transformed for human use. These ethical considerations don't make interstellar travel impossible in a physical sense, but they do add another layer of difficulty to an already nearly insurmountable challenge. Any realistic interstellar mission would need to address these questions satisfactorily, building consensus across diverse populations with different values and perspectives. That's perhaps as difficult as solving the technical challenges. Now let's consider one final technical challenge we haven't fully explored: the problem of stellar dynamics and mission planning. Stars don't stay in fixed positions, they orbit the galactic center, each following its own path. The Sun orbits the Milky Way roughly once every 225 million years at a speed of about 220 kilometers per second relative to the galactic center. Other stars have their own velocities. Proxima Centauri is moving relative to the Sun at about 22 kilometers per second. It's actually approaching us. In about 27,000 years, it will reach its closest point at about 3.1 light-years, then begin moving away. This relative motion matters enormously for mission planning. If your journey takes centuries, you can't aim for where Proxima Centauri is now. You need to aim for where it will be when you arrive. This is like trying to throw a ball to someone who's running, except the someone is light years away and the ball takes decades to arrive. The calculations require precise knowledge of stellar velocities and positions, accounting for gravitational perturbations from other stars and the overall galactic potential. Small errors compound over long journeys. If your estimate of Proxima Centauri's velocity is off by even 1 kilometer per second, over a century-long journey, that error translates to a missed distance of over 3 billion kilometers, 20 times the Earth-Sun distance. We can measure stellar velocities using Doppler spectroscopy, observing how starlight is shifted toward red or blue wavelengths due to motion toward or away from us. Modern telescopes like Gaia, launched by the European Space Agency in 2013, have measured the positions and velocities of over 1 billion stars with unprecedented precision. Gaia's third data release in 2022 provided proper motions, angular velocities across the sky, for stars throughout our galactic neighborhood. But even Gaia's measurements have uncertainties, and those uncertainties grow when you try to predict positions decades or centuries into the future. You also need to account for undiscovered stellar companions. Many stars we think are solitary might actually be part of binary or multiple star systems, with companions too faint to detect. These hidden companions exert gravitational influences that alter the star's motion in ways we can't predict if we don't know they exist. There's also the three-body problem, one of the classic challenges in physics. While we can precisely calculate the orbital motion of two bodies under gravity, the Earth and Moon for instance, adding a third body makes the system chaotic. Tiny changes in initial conditions lead to vastly different outcomes over time. When you're planning a journey through a region of space containing numerous stars, each exerting gravitational influence, you're dealing with a many-body problem that's even more complex. Long-term trajectory predictions become increasingly uncertain. All of this creates another barrier. Even if you could solve propulsion, energy, shielding, life support, and all the other challenges, you'd still face profound difficulty in simply getting to your intended destination. Space is not a static background, but a dynamic environment where everything is moving. Successfully navigating that environment over interstellar distances and timescales requires precision that might be fundamentally unachievable. Let's take a moment to step back and consider what all of this means from a broader perspective. We live in an age where technology has given us capabilities that would seem like magic to our ancestors. We've walked on the moon, we've sent probes to every planet in our solar system, we've photographed the supermassive black hole at the center of our galaxy, we've detected gravitational waves from colliding black holes a billion light-years away, we've found thousands of planets orbiting other stars. These achievements are genuinely miraculous, testaments to human ingenuity, curiosity, and determination. They demonstrate that when we commit ourselves to understanding and exploring the universe, we can accomplish extraordinary things. It's natural to assume that this trajectory will continue, that the challenges we face today will eventually yield to future technology just as past challenges have yielded to us. But there's a dangerous trap in that assumption. Not all barriers are temporary, not all problems have solutions. Some limits might be fundamental features of physical reality that no amount of cleverness or technology can overcome. The speed of light appears to be such a limit. The exponential nature of the rocket equation might be another. The vast distances between stars might be insurmountable, not because we lack ingenuity, but because the universe is structured in a way that makes them insurmountable. This is a hard truth to accept, especially for a species as ambitious and exploratory as humanity. We want to believe that the stars are within reach, that the galaxy will eventually be ours to explore. Science fiction has painted vivid pictures of star-faring civilizations, casual travel between star systems, galactic empires, and federations. These stories inspire us, fuel our dreams, motivate young people to study science and engineering. But dreams, no matter how beautiful, don't override physics. The universe operates according to laws that we didn't write and can't rewrite. Our hopes and desires, our sense of destiny, our belief that humanity is meant to spread among the stars, none of this changes the fact that traveling even to our nearest stellar neighbors would require overcoming barriers so extreme that they might be impassable. Does this mean we should give up? Should we abandon hope of ever reaching the stars and resign ourselves to remaining confined to one small planet, orbiting one ordinary star? Not necessarily, but it does mean we should be realistic about the challenges and honest about the odds. We should pursue interstellar travel research if we want to, but we shouldn't assume success is inevitable or even likely. We shouldn't make decisions about humanity's future, how we organize our civilization, how we allocate resources, what goals we pursue, based on the assumption that we'll someday spread to other star systems. Instead, we should focus on what we know we can do. We can explore our solar system thoroughly. We can establish permanent settlements on the Moon and Mars. We can mine asteroids for resources. We can build space habitats at Lagrange points. We can construct enormous space telescopes that let us study the universe in unprecedented detail. We can search for signals from other civilizations, even if we can't visit them. We can make our home planet more sustainable and resilient. We can work to ensure that human civilization persists for millions of years in our solar system, creating a rich, vibrant, technologically advanced culture that explores and understands the cosmos, even if we can't physically traverse it. There's something else worth considering. Maybe the journey is more important than the destination. The effort to develop interstellar travel technology, even if it ultimately fails, drives innovation across countless fields. Research into advanced propulsion benefits satellite technology and solar system exploration. Work on closed-loop life support systems helps us build sustainable habitats on Earth and in near-Earth space. Advances in materials, science, artificial intelligence, robotics, energy generation, all these emerge from wrestling with the challenges of space exploration, even when the ultimate goal remains out of reach. Perhaps interstellar travel serves humanity best as an aspirational goal, something we work toward knowing we may never achieve, but which pulls us forward and upward, encouraging us to push the boundaries of knowledge and capability. Like a mathematical proof that remains unproven or a philosophical question that has no definitive answer, the challenge of reaching the stars might be valuable precisely because it's so difficult, because striving toward it makes us better, smarter, more capable. Even if we never fully succeed, there's also the possibility, remote but not impossible, that we're wrong, that some breakthrough we can't currently imagine will change everything, that our descendants will look back at this discussion the way we look back at predictions from the 19th century that humans could never fly or that computers would never be practical. History is full of experts declaring things impossible shortly before they become reality. But here's the crucial difference. Those past impossibilities were declared impossible based on incomplete understanding or failure of imagination. People said humans couldn't fly because they didn't understand aerodynamics. They said computers would be impractical because they imagined only the room-sized vacuum tube machines of the early computing era, not the transistors and integrated circuits that would follow. In each case, the barrier wasn't fundamental physics, but merely current technology and understanding. The barriers to interstellar travel are different. They're rooted in well-established physics that's been tested countless times. Special relativity, the rocket equation, thermodynamics, the finite speed of light. These aren't gaps in knowledge but confirmed features of reality. Overcoming them would require not just better technology but a fundamental revision of physics at a level that would make relativity and quantum mechanics look like minor corrections to Newtonian mechanics. That's not impossible, but it's also not something we should count on. So where does this leave us? If interstellar travel is effectively impossible, what does that mean for humanity's future? Are we truly trapped in our solar system, destined to forever gaze at the stars we can never touch? In one sense, yes. The universe appears to be structured in a way that confines civilizations to their home star systems. The distances are too vast, the energy requirements too extreme, the speeds too limited. We are quite possibly permanent residents of the solar system, able to observe the cosmos but not to physically explore it beyond our local neighborhood. But perhaps trapped is the wrong word. Our solar system is enormous. It contains vast resources, countless worlds to explore, room for human civilization to grow and diversify for millions or billions of years. The sun won't die for another 5 billion years. The planets, moons, and asteroids offer endless opportunities for exploration, settlement, and development. We could build rotating space habitats housing billions of people in comfortable Earth-like environments. We could establish research stations throughout the solar system, studying every world in detail. We could develop our technology and knowledge to extraordinary levels, creating a civilization that, while confined to one star system, is rich, diverse, and enduring. We could also engage with the broader universe in other ways. We could continue searching for signs of other civilizations, establishing communication if we find them. Radio conversations taking decades or centuries per exchange wouldn't satisfy our desire for immediate contact, but they could still be profoundly meaningful. Knowing we're not alone, exchanging ideas and knowledge with other intelligences, building a community of civilizations connected by light-speed communication, this could be humanity's role in the cosmos, even if we never leave our star. We could continue studying the universe with ever more powerful instruments, unraveling its mysteries, understanding the fundamental nature of reality. We could create art, philosophy, science, culture of extraordinary depth and sophistication. We could develop virtual realities as rich and complex as physical reality, creating entire universes limited only by imagination. We could explore inner space, consciousness, intelligence, meaning as deeply as we explore outer space. In short, confinement to our solar system, if that's what the universe imposes, doesn't mean stagnation or limitation in any meaningful sense. It simply means we're playing a different game than we imagined, with different rules and different possibilities. And who knows, maybe we'll find evidence of other civilizations facing the same barriers. Maybe we'll discover that the galaxy is full of intelligent species, each confined to their home systems, each observing the others from afar, each wondering if they're alone. Maybe the universe is structured this way deliberately, if you believe in design, to encourage diversity, to let countless civilizations develop independently, to create a cosmos rich with variation, rather than one homogenized by easy interstellar travel. Or maybe, just maybe, there is a way. Maybe somewhere in the gaps of our knowledge, in the frontiers of physics we haven't yet explored, in the unexpected discoveries still to come, there's a path to the stars. Maybe not in our lifetimes, maybe not for centuries, but eventually. It's a slim hope based on no concrete evidence, requiring multiple breakthrough discoveries that may never come. But it's not completely impossible. The universe has surprised us before. Quantum mechanics seemed absurd when first proposed. Particles in multiple places simultaneously, measurement affecting reality, entanglement connecting distant objects. Yet it turned out to be true, confirmed by countless experiments. General relativity predicted bizarre phenomena, time dilation, gravitational waves, black holes, that seemed like mathematical curiosities until we observed them directly. Reality is often stranger than we expect. So while we should be realistic about the immense challenges of interstellar travel, while we should make plans and decisions based on what we know is possible rather than what we hope might be possible, we shouldn't completely close the door. We should continue researching, exploring, pushing boundaries. We should study advanced propulsion concepts, not because they'll definitely work, but because the attempt expands knowledge. We should search for loopholes in physics, not because we expect to find them, but because questioning assumptions is how science progresses. At the same time, we should appreciate what we have. Earth is a jewel, perhaps the only living world within light years. Our solar system is a vast frontier, enough to keep humanity busy for millions of years. The universe, even if we can't physically traverse it, is endlessly fascinating to study and contemplate. These are gifts of extraordinary value, not consolation prizes. The stars may be unreachable, but they're not meaningless. They remind us of the vastness of existence, our small but significant place in the cosmos, the limits of our power, and the boundlessness of our curiosity. They inspire wonder, which is perhaps the most valuable thing they can give us, and they pose a challenge, one that might not be solvable, but which makes us better for trying. Whether humanity eventually reaches the stars or remains forever in our solar system, the journey of discovery continues. We continue to learn, to grow, to push against the boundaries of the possible. We continue to ask questions, even when the answers are sobering. We continue to dream, even when reality constrains those dreams. That's what makes us human. That's what makes us explorers, even if the territories we explore are ultimately more limited than we once imagined. The universe has placed the stars tantalizingly before us, visible but untouchable, like reflections in water that scatter when you reach for them. Whether that's a cruel joke, a profound test, or simply the way things are doesn't really matter. What matters is how we respond. Do we give in to despair, or do we find meaning and purpose within the constraints we face? Do we abandon exploration, or do we explore what's actually within reach? Do we let the impossible define us, or do we let the possible inspire us? These are the real questions. And unlike the question of whether we'll ever reach Alpha Centauri, these questions have answers we can actually control. The challenges of interstellar travel reveal fundamental truths about our place in the universe and the physical barriers that may keep us confined to our cosmic neighborhood forever. If you found this deep dive fascinating and want to explore the scientific details, stunning visualizations, and the profound implications of humanity's potential cosmic isolation, I invite you to watch my comprehensive video, "This is Why We Are Stuck in the Milky Way Forever." The video is at the left side of the screen. See you there.